Hello folks. In the last video we made a brief introduction to electronics class. We introduced two new materials other than the intrinsic silicon semiconductor, N-type and P-type materials. N-type material had excess electrons, lots of electrons in it, and P-type material had lack of electrons, shortage of electrons, or namely holes in it. Okay, so what happens when you bring two materials, P-type and N-type materials, right next to each other? One of them has lots and lots of free electrons. The other one has lots and lots of holes. So it has lots and lots of lack of electrons. There will be a concentration difference. So we have lots of electrons here. We have a place that is hungry for electrons here. So what happens is electrons will start to flow from N side to P side. Of course, this is not a closed circuit. So this concentration, this flow of electrons, this current, should not last forever. This is the diffusion current. And this is because of the concentration difference of these electrons. Okay, so at some point, this current should be balanced by another current. And what happens is, right at the junction of P and N-type materials, and the P side, where we have lots of holes, right next to this junction, we will have a small place where we have lots of electrons. Okay, we have more electrons than the holes right next to the junction. Okay, and likewise in the N side, where we have lots and lots of electrons, right next to this junction, we will have a little place where we have lots and lots of holes instead of electrons. Okay, so what happens is, right close to this junction, we will have an electric field going from the N side to the P side. So because of this electric field, we will have electrons going from this side to this side. This is called the drift current. At some point, this drift current will be balanced by the diffusion current, which was occurred because of this electron difference. They will be balanced. So the electrons going from here to here because of this drift current will be balanced by the diffusion current, which is going from this side to this side because of the concentration difference. And at that stable point, as you can see, in order to generate this electric field, we will have a potential difference. The potential at this point should be higher than this potential at this point. So there will be a built-in potential difference between the N side and the P side. This potential difference will be right close to this junction. And this little area where there is a built-in potential difference is called the depletion region. Okay, now this built-in potential is affected by a number of factors. First of all, how many acceptors in the P side there are, and how many donors there are in the N side, and what are the number of free electrons in the intrinsic semiconductor, that is Ni, okay, and the temperature. As you can see, the formula for the built-in potential is Kt over Q ln Na times Nd over Ni squared. Now, K is Boltzmann constant. It's a constant number. T depends only on the temperature. So T is 300 kelvins in the room temperature. Q, magnitude of electron charge. So that's a constant number. So Kt over Q only depends on the temperature. It's called Vt. Kt over Q is called Vt, the thermal voltage, okay, which is roughly equal to 26 millivolts at 300 Kelvin. Now, ln Na, number of acceptors in the p side, Nd, number of donors of electrons in the n side. Ni squared is the number of free electrons and free holes in the intrinsic silicon semiconductor. So if we give an example, if Na is 10 to the 16, Nd is 10 to the 16 per centimeter cube. So there are 10 to the 16 free electrons and free holes in a centimeter cube in the p side and n sides. Okay, at 300 Kelvin, what is VBI? What is this barrier over here? Okay, VBI is VT KT over Q, so 26 millivolts. This is in volts here. Ln 10 to the power of 16, 10 to the 16, 1.5 times 10 to the 10 squared, and that is equal to roughly 0.7 volts. Okay. If we use germanium diodes instead of silicon diodes, this Ni will be different, and these NAs and NDs for germanium diode is different. So we will get roughly around 0.3 volts VBI for germanium diodes. So it's different for different types of diodes. So far, we haven't applied any voltage across this PN junction, and nothing interesting is happening so far. What happens when we apply a voltage that is higher in the N side? So this is the P side, this is the N side. I'm applying a voltage that is higher on the N side. Now, here in the symbol, this is the P side, this is the N side, and we are applying a voltage that is higher on this side. What happens is we already have this barrier, VBI, and we are applying a larger voltage here. So this barrier is going up. So we go up here. This place right here is VR. Okay. So if we have VR is equal to 3 volts, for example, we will be raising this area 3 volts higher. Okay. What happens is when we apply more voltage here, this depletion region is getting wider. Okay, and this electric field will be getting higher, but there will be no current flowing, because the only thing that voltage VR is doing is raising this gap. Okay, so there will be no current when we raise that gap. Okay, the only thing that's happening is if we have a capacitance from this point to this point, since the depletion region is getting bigger, that space is now wider, and that's, if that depletion region is getting wider, that means we have less depletion region capacitance. Okay, so if we have the depletion region capacitance here, all we are doing is making that depletion region capacitance smaller. So now we can use the diode as a capacitor whose value can be controlled by the voltage value. Okay, if we increase the voltage value, we are making the capacitor value smaller. Okay, now of course we cannot raise this voltage to infinity. At some point this depletion region will go all the way here. Okay, now if we try to increase the voltage more, all we will be doing is breaking the diode, and this will be non-reversible. So if we just break the diode, we will not be able to use that diode anymore. Okay, now what happens if we apply more voltage on this side? Okay, if we are raising this voltage, let's see what we are doing. We have a 0.7 voltage difference here. If we apply more voltage here, we will be making this gap smaller. If we apply 0.1 volt, for example, VD is 0.1 volt, we will make this barrier 0.1 volt smaller. Okay, increasing VD will decrease this gap. Okay, decrease this barrier. At some point, there will be no barrier. Okay, so up until VD is equal to VBI, up until this point, when we increase VD, we will be decreasing the electric field, we will be decreasing the depletion region, but there will be small current, if not no current. Okay. At VD is equal to VBI, there will be no depletion region and there will be no barrier. If we try to increase the voltage more than VBI, there will be current. Okay. Well, actually, what happens is you are destroying the whole barrier. Okay, so there is no barrier for the electron flow, so it will act like a short circuit now. So little voltage difference will make a big difference in the current value. Okay, let's draw the IV graph associated with the diodes now. First we need to define the conventions. VD is defined as the voltage from the P side of the diode to N side of the diode, and ID is defined as current that is flowing from the P side of the diode to N side of the diode. Now, if VD is here and ID is here, VD negative means the voltage at the N side is higher than the voltage at the P side. So if we increase the voltage more in the negative side, we were actually making the voltage barrier higher and higher and higher. At some point, our diode will be broken. Okay, and that's a non-reversible case here. Now, if we apply a positive voltage, means this voltage here in the P side is higher than the voltage at the N side, we were actually making that voltage barrier lower and lower and lower, and at VD is equal to VBI, there was actually no voltage barrier between the P and N sides. Okay, and very little voltage difference makes a big difference in the current. Okay, so it was actually acting like a short circuit now. Okay, now scientists found that ID and VD obey this rule. ID is equal to IS times exponential VD over NVT minus 1. Now here ID and VD, as you can see, are related in this exponential formula. Okay, now IS here is the saturation current, reverse saturation current. As I said before, there is actually very small current here, and that the small current is called the IS. Okay, that's on the order of 10 to the minus 15 to 10 to the minus 13 amps. Very little current is actually flowing. And here N is the ideality factor. That's a constant number between 1 and 3. And VT was the terminal voltage, which was actually 26 millivolts, roughly around 26 millivolts at 300 Kelvin room temperature. As you can see, ID and VD are exponentially related, and exponentially related functions are hard to evaluate. So if we eliminate this minus 1 here, the reason why we have minus 1 is because of this little current here. So if we ignore that minus 1, and if we take the ln natural logarithm of both sides, we have ln ID is equal to ln IS. This times turns into a plus sign in the natural logarithm. We have ln exponential VD over NVT. Ln and exponential cancels out, so we have VD times 1 over NVT here. So as you can see, ln ID and VD are linearly related to each other. So if we draw VD versus ln ID graph, as you can see, when VD is equal to 0, we have ln ID is equal to ln IS here, and the slope of this graph is 1 over NVT. So for example, if you want to find the characteristic of a diode, we need to find two numbers, IS and N. How can we find IS and N? What we can do is, in the lab, we can go and apply different voltages here, okay, and we can find corresponding ln ID values here. For example, we can find 10 VD values and we can find 10 corresponding ln ID values. We draw this linear graph, okay, and then we can find ln IS and N values here, okay. So in this video we talked about the diode physics. In the next video we will be starting to use diodes in the real circuit.